Hello, this video is on entropy. Now there are two driving forces that allow chemical reactions to be spontaneous or to go forward or not. And one is enthalpy, that was the last video, and this is entropy or degree of randomness. Okay, so in nature it's easier to be random than it is to be ordered. Nature favors an increase in entropy. So there are a couple different ways of dealing with entropy, determining whether a reaction is increasing entropy or decreasing. One is just by looking at it. So there are a couple reactions here that I want you to just take a look at. Whoops. 1 and 2. So let's take a look at the first one. We have sodium bicarbonate, solid, yields CO2 gas plus H2O gas plus sodium carbonate, solid. So what we're going to do is take a look at just the moles, the number of moles. You know, if you're producing more stuff, there's more ways to order that, and therefore it's more random by nature. So if we take a look at this, we're going from 2 to basically 1, 2, 3. Okay, so we're going from 2 moles to 3 moles. So that in itself tells you that randomness is increasing, but take a look at also the states of matter. We're going from a solid, very ordered, to a gas, very non-ordered, another gas, and another solid. So by looking at those two things, by looking at the number of moles and looking at the states of matter, in this case we can say that our randomness is increasing. So randomness is S, and 0 just means the states that it's at standard states, 25 degrees. Basically that one is increasing, and we can also say that one's favored. Okay, I'll take a look at the second one just by eyeballing it. We go basically from 1 mole to, or 3 moles, that's 4 moles, to 2 moles. So we're decreasing the number of moles, decreasing the amount of stuff, and therefore by nature that's more ordered, and therefore we'll have to say that entropy is decreasing, and that'd be not favored by nature. Okay, looking at reactions is all fine and dandy, but a lot of times we'll need numbers. And so on your thermodata resource sheet, in the second column there's entropies, and what we can do is the same thing we did with enthalpy, which is set it up so our products, if we look at all the entropies of our products and we subtract all the entropies of our reactants, that will give us a change in entropy. So let's take a look at it in terms of this reaction. This is the same reaction you had on the enthalpy worksheet. I also have to say that hexane is not on that worksheet, that data sheet. So you'll have to look it up. Google has all that stuff, so just look it up online. So I'm going to take, in this case, 14 waters times 69.91. We'll say that's H2O, plus 12 times CO2, which is, let's see, 213.74. Just a sec, we'll talk about the units. We're going to subtract that, all the reactants. So 2 times, this is the one I had to look up, 295, plus 19 times O2, which is 161.06. Unlike enthalpies where your elements are 0, have no heats of formation, entropies, they always have some sort of entropy, because molecules can always be twisted and tugged and bent, and therefore there's always a degree of randomness that they have. So if we take a look at this side, we end up having 3,543.62. Now right now I'm going to introduce those units to you. It's joules per mole times K. So there's a temperature variable in there somewhere, and we'll take a look at that a little later. And then minus 3,650.14 joules per mole. Okay. That's going to equal negative 106.52 joules per mole. Okay. Now we can take a look at it. If you take a look at this reaction, just eyeball it. So we're back up here. If we just eyeball this, you might say, well, can I just look at it and tell? We're going from 19 gases to 12 gases. We're going from 2 liquids to 14 liquids. It's hard to tell. You might go either way on this one. Well, this number tells us specifically that entropy is decreasing. So delta S in this case is negative 106.52. Nature, at least in terms of entropy, doesn't favor this reaction. I hope that helps, and take care.